TCP and UDP stands for Transmission Control Protocol and User Datagram Protocol. We're going to talk about these. These are the way that data is transferred over your network. So Transmission Control Protocol. The big thing you want to remember for TCP is it is a connection-oriented protocol. So what happens is when you want to talk to a server like Facebook, you go through a three-way handshake, and it does what's called the SYN-ACK. And so what happens is I go, hey Nick, I want to talk to you. And Nick goes, I acknowledge you want to talk to me. I say, okay, I'm ready to talk to you. And then I start sending him my data. So you have this three-way handshake to make sure both parties are ready. This gives us reliable transportation of all of our segments. So if in the middle of me sending my data to Nick, he can go, oh, wait a minute, I didn't get it. He can realize that. It's kind of like if I was going to send him a book, right? There's 100 pages in the book. Each book page has a number. And when I send it to him, I send him the first 10 pages. I go, did you get those 10? He goes, yeah, I got those 10. So I sent him another 10. And he goes, oh, I only got 9 of those. Oh, what are you missing? I'm missing page 17. I'll resend page 17, right? And so that way he can make sure he gets the entire book. He's not missing any pages. This is good for all types of network data, and especially stuff that needs to be assured to get where it's going. So if you're going to your bank, you want to make sure that the right information is being sent back and forth. TCP will do that for you. And again, the nice thing about this stuff is it's all handled at the network layer for us, it's all handled by the network for us. You as a technician don't need to configure it and say, I want to use TCP today, or I want to use UDP today. It's going to choose that based on the design of the network by the folks. For us as network technicians to understand that TCP is this three-way handshake and it's reliable, guaranteed transmissions, that's what you really need to know about it. The other side of the coin is UDP, and UDP is User Datagram Protocol. Now this one we call the connectionless protocol. This is unreliable. It just sends stuff and hopes it gets there. It's it's unaware if anything got there or not. It just sends it and forgets it, okay? There's no retransmission at all. It's really good for audio and video streaming because it has a very low overhead. Because there's no three-way handshake, there's no checking of the data. That all saves us bandwidth. We don't have to go back and do it over and over again. The reason why it's good for audio and video is because A, it's faster, but B, if you miss 1 or 2 packets inside of a video, the videos are such large file sizes, your video will still play just fine, right? Whereas if I'm going to show you maybe a single picture, if I'm missing a chunk of that, you might visually see it. So audio and video, you're not really going to notice if you're missing some pieces, right? It's just going to send it and forget it. So as the picture says here, right, it says, hey, are you getting this? And the other guy goes, I don't care, just send it faster. That's what UDP is all about. Just send it to me faster, send it, send it, send it. When I teach a lot of times, especially in a large class, it's kind of UDP, right? I put it out there and hopefully you're getting what I'm saying. I have no way to really know if you're all getting what I'm saying. If we were doing TCP, it might be more of a hands-on tutoring session where it's, just me and Chuck, and I'm like, hey Chuck, are you getting this as we're going? And that would be no problem, right? So that's the way that TCP versus UDP works, right? TCP, very hands-on. We check it the whole time. UDP, fire and forget. So this is just a nice little summary chart of what we're talking about, right? We have this connection-oriented protocol at top with TCP. UDP, we just send it on over. There's no connection. TCP is reliable. UDP is not reliable. With TCP, we can retransmit if things are missed. With UDP, we just fire and forget. We have no way to send it to you again. With TCP, we have segment sequencing. What that means is when I send something to you, like that book I was sending him, that I'm sending it 10 pages at a time, if I put it in the mail system, is it going to take the same route every time it gets to him? No, it might take different roads to get there. It might be traffic one day. But when he gets it, he can put them back in order because he has page numbers on all of those. With UDP, it can take different routes, but if it gets there at different times, he's going to read it in different orders, okay? So TCP allows us to put it back in order. UDP, we have no sequencing. It just gets there the order it gets there. And again, with TCP, we acknowledge the segment, say, yes, I got those 10 pages. UDP, it's just going to get there if it gets there, and if it doesn't, you're not going to get it. There's no acknowledgement. There is no resending it. So windowing. With TCP, we have a thing called windowing. And what it does is it allows the clients to negotiate how much data is going to be sent in each segment. So again, like we'll use that book example, and send that 100 pages back there to Nick. What I'll do is I'll start out giving him 10 pages. And he'll go, hey, did you get all 10? He'll go, yep, I got all 10. I'll go, cool. Let me try 15. Did you get all 15? Yep, I got all 15. Cool, let me try 20. And I keep increasing my window size to see if he still gets them all. And if I get upward, And I get sad and sending him 25 at a time. He goes, oh no, I only got 22 of those. Well, maybe I was talking too fast. Let me slow it back down and then go back to 20. And so we're constantly adjusting this window to send as many as we can between acknowledgements without sending too many, because every time I go to send him one and I miss an acknowledgement, I have to send the entire thing again. So it's good to send big bulk packages, but if he loses the package, I gotta send a big bulk package again. So we constantly are adjusting how much is fitting in each package. That's all windowing is doing for us. We adjust upward and lower. If we have to retransmit a lot, we start going smaller and smaller packages. If we're getting it all, we'll keep going upward and upward until we have errors. As we keep adjusting to push as much as we can, as quickly as we can, without having too many errors. So buffering. Some devices like our routers have memory on them that allocate the ability to store these segments until bandwidth is ready, okay? So when it's available, it'll start sending out the information in the buffer. If the buffer overflows, the segments will be dropped. Why this becomes important, right? We talked about Cat5e networks before, right? So we said, hey, inside your network, you're using 1 gigabit per second connections, like from A to the router and B to the router. But our internet provider here with the C might be Comcast or Verizon, and maybe we're only paying for a 62 megabit per second connection. Or like in my house, we need a 75 megabit per second connection. If I'm sending things to the router at 1 gigabit, which is 1,000 megabytes per second, but the router can only send it to the internet at 75, or in this case 62.5, what ends up happening? You get a backup, right? And so what ends up happening is the router has to have memory to hold the extra data. And what it does is it holds it until it has room to send it. Now, why this works without having problems all the time is that you're not usually sending 1 gigabit per second of data continually over the network 24 hours a day, 7 days a week, right? If you were, you would end up overloading this buffer and segments will be dropped. So instead, as I'm going to Facebook, I might overload it for a couple of seconds. The memory will hold it. When there's room, it'll send it out. Okay? That's all buffering is doing. It's just holding it until you have room to send it out the rest of the way. Port ranges. So one of the things you do need to understand for CompTIA is you have to know port numbers, okay? So our ports, what they are is they could be anywhere from 0 up to 65,536. We have what's called well-known or reserved port numbers. Those are the ones that are 1,024 or lower, 0 to 124. The ones above 1,024, all the way to 65,000, are called ephemeral ports. Those are ones that are not already designated for another purpose. So you can use those as you need to. And I'll show you the ones that you have to memorize. There's certain ones we're going to have to memorize. This next table is something you're going to have to memorize for the exam. And I'll make sure you guys each a printout of it. So with the port numbers, we have different services listed here with the acronym and what they are and the port numbers. So they may ask you on the exam, if you want to do a file transfer, what port would that happen over? Well, FTP is the file transfer protocol. It operates on port 21. If you wanted to have secure remote access, that's SSH, it operates over port 22. If you want to do unsecured remote access, it's port 23 for Telnet. If you're going to send emails, it happens over port 25, etc., all the way down the list, right? What a port number is, the reason I have a picture of a door here is because that's what port numbers are. They are a doorway. So I have one IP number for this laptop, but I might be going to 3 or 4 websites at the same time. How does it know which browser tab is going to Facebook and Google and Yahoo? It uses port numbers. In this case, we'd use high number ephemeral ports to keep that separated. So make sure you do understand what the service is, what the acronym is, and what the IP is. Unfortunately, this is just a memorization chart, right? Every IT certification you ever take for the rest of your life, you're going to have to know port numbers. This is the basic ones you're going to have to know. As you go into other certs, they're going to add more. And they'll add more, and they'll add more, and they'll add more. When you get into CEH, there's about 30 to 40 of them you have to know. When you go to CISSP, it's about 30, 40, 50 of them you have to know, somewhere in there. And so they just keep adding more and more. These are by far the most common ones, which is why A+ uses them. So when we send data over the network, if I'm going to go from the client to the web server, I am going to call out to the web server on port 80, which is web traffic. So that's my destination port. 172.16.1.2 is the IP of the server. The port is port 80. I called it from a high number port, in this case 1248, just a random high port, something higher than 1024, right? When the server replies, it's going to send it back to me on port 1248. When my computer gets that, it goes, oh, that was your connection you asked for Facebook, and sends that information to my web browser. That's how it keeps these streams of data over the same network pipe separated by using these ports. So network address translation and port address translation. Network address translation is used to conserve our limited supply of IPv4 addresses. If you guys remember when the last lecture we talked about public and private addresses, what NAT does is it takes our private address and converts it into a public address. So I'll give you a good example of this. In this particular picture, we have an IP address of 192.168.1.24. That is a private Class C address, right? If we want to go on the internet, we might use the address of 66.12.13.54 that was given us by our cable provider. So what happens is my computer goes to the router then transfers the information using the other address out to the internet and back. Now with NAT, you have to have a one-to-one mapping of IP addresses. So if I have one address from Verizon, I can only have one device on that address, which doesn't really work well if you have a house with a wife and 2 kids and a bunch of game systems and everything else, right? So what we use, the newer version, is called port address translation. And what that does is it uses port numbers instead of IP addresses for the translation. So in this case, you can see in the picture I have 4 different devices. When they call out, they're going to call out from the same IP, the 66.12.13.54, but they're going to append a port number to it. And that will allow them to go out to the internet using that port number. When it comes back with the response based on that port number, it'll know which computer in the room it was talking to. Okay? I'll show you a picture of that as well later. So, a couple of different ways that we can do address translation. We have dynamic NAT, where we have a pool of IP addresses that are public and a pool of ones that are private, and we do a one-to-one mapping. The only benefit here is from a security standpoint because people won't know your public and your private IPs. Static NAT, we do a one-to-one mapping, and it's actually 1-for-1, so we don't have to have a pool, it's just statically assigned. But what we really use nowadays, like I said, was PAT, which is port address translation. This is what you're going to use in your small office, home office network. We can use multiple private IP addresses sharing one public IP. So for instance, you can have a many-to-one translation. It's very common in small networks. In your house, you have a Class C address that can handle 254 hosts on that machine, but you only have one public IP. And so when your kid goes out to the internet and you go out to the internet at the same time, you both are using the same IP address on the internet, but it's separated by port number. And that's how it keeps track of who is using which service. And here's a picture of how that works. So you can see here, this is a NAT. This is using network address translation, not port address translation. So if you notice here, when this client up here calls out to this server over here, source and destination, it hits the router changes this internal address, this 10.1.1.1, which is a private IP, into 17.17.1.101, which is a public IP. That's all we're doing with NAT. We're translating a public or a private to a public or a public to a private. Now what you use at home looks more like this. This is PAT. And what happens here is you can see that this guy, 10.1.1.1, has a port number of 1025, which is an ephemeral port, a high port, and he's going to a web server on port 80. When he hits the router, it uses the public IP with a port number to keep track of his connection. Notice that the second guy is also going to a web server, and he chose a different port number to call on. And when he gets to the router, he's using the same public IP, but a different port number, which allows this server to know that these are 2 separate connections even though they're coming from the same place. Okay? That's how your modem works at home. When your router at home keeps track of all of your public and private connections. It uses PAT to do that. So if you have a customer who requires that both the default FTP ports be allowed on the firewall, which of the following should the technician enable to allow this communication? So this comes down to basically, did you memorize your chart, which we haven't yet because I didn't give you enough time to, right? But FTP is port 21. It also runs on port 20 for data. And this is a TCP connection because we're going to do file transfers. We want to do a three-way handshake. So for us, the answer would be port 20 over TCP and port 21 over TCP. Okay? Port 22 is used for SSH. It's a different service. It's not going to do file transfers for us. So it's just, again, like I said, you have to apply that chart that we memorize into this. And this is one of the more difficult ones because they actually asked you the TCP versus UDP as well. Normally, they're just going to ask you for the actual port number.